Okay, so now I want you to compare the two sides, okay? And what I want you to notice, for example, is the Poisson bracket of A with B is minus the Poisson bracket of B with A. The commutator of A with B is minus the commutator of B with A. Also, the Poisson bracket of AB with C is the Poisson bracket of AC with B plus A times the Poisson bracket of B with C. And the commutator of AB with C is the commutator of A with C times B plus A times the commutator of B with C. So can you see that the algebraic structure of Poisson brackets matches that of commutators? Let me just write down one more equation that you can check very easily. If you've got the Poisson bracket of A plus B with C, this is actually the Poisson bracket of A with C plus the Poisson bracket of B with C. And this matches the fact that the commutator of A plus B with C is the commutator of A with C plus the commutator of B with C. So again, an exact match. And what you'll find is any algebraic equation that you write in terms of the commutators, in terms of the Poisson brackets, the corresponding equation in terms of the commutators agrees completely. Now look at the first two equations. The Poisson bracket of x comma p was 1, but the commutator of x and p is IH bar. The Poisson bracket of p with x is minus 1, but the commutator of p with x is minus IH bar. And that's again a general rule. If you've got the value of the Poisson bracket, you just multiply by IH bar to get the value of the commutator. So here's an example of that rule. If we've got the ODT is equal to the Poisson bracket of O with H, well, like I told you, you replace the Poisson bracket with the commutator, and the value is IH bar times by the value that you had for the Poisson bracket. And what you see is the classical equation of motion written in terms of Poisson brackets exactly reproduces the Heisenberg equation of motion written in terms of commutators. Now, you can rewrite all of classical mechanics in terms of just the Hamiltonian and Poisson brackets. So together with the Hamiltonian and Poisson brackets, you can write every equation of classical mechanics. And then, if you want to go to the quantum theory, if you've got some Poisson bracket equation, let's say A comma B is equal to C, to get to the quantum theory, you just replace the Poisson bracket by a commutator, and the value of the Poisson bracket is multiplied by IH bar. And this captures all of quantum mechanics. So for example, x and p, which used to be commuting functions, you could specify x and p simultaneously, they become operators that don't commute. So you can no longer fix the value of x and p. So you've caught in this rule the fact that the Heisenberg uncertainty principle, the fact that you can't measure simultaneously the position and momentum of the particle. So this here is a very simple rule to take any classical theory and promote it to a quantum theory. And this was discovered by Dirac, and it's called Dirac's correspondence principle. Now, I just want to do one thing, one slight generalization, just to make sure that we understand what we're doing, and that is, how would things look if we were working in 3 dimensions? Well, in that situation, the Hamiltonian would be a function of an x component of momentum, a y component of momentum, and a z component of momentum. And it would also be a function of the 3 coordinates x, y, and z. What's more important is, what would the Poisson bracket be? And what the Poisson bracket would look like here, px would be conjugate to x. So we would have dA dx, dB dpx minus dA dpx, dB dx. Then we would have an equation like that for each conjugate pair. So we would have plus dA dy, dB dpy minus dA dpy, dB dy, and then finally the same thing, but now for the z's. dA dz, dB dpz minus dA dpz, dB dz. And in fact, your phase space will always come with an even number of variables. Each variable will have a conjugate, and then the Poisson bracket would be given by a sum of terms like this, one for each conjugate pair. And if you wanted to get the quantum theory, just take your Poisson brackets and promote them to commutators. This rule of promoting Poisson brackets to commutators by Dirac's correspondence principle, this is what is called canonical quantization. Canonical quantization. So what I want to do next is we're going to develop the Euler-Lagrange equations for fields. And the reason why we're going to do that is we know we want a Lorentz invariant theory. So we're going to explore how to write down a Lorentz invariant action. And that's something simple that we'll be able to understand. Once we've written down the Lagrangian formulation, we'll be able to derive the Hamiltonian formulation. We'll be able to write it in terms of Poisson brackets. And then we'll be able to quantize by promoting the Poisson brackets to commutators by canonical quantization. And what I want to show you is that for the free field, we will reproduce the field that we obtained a few chapters ago. Okay, so we'll reproduce our free scalar field. Now, the point of this exercise is that although we were able to get our free scalar field by a very physical method, writing down some axioms, as soon as we switch on interactions, we can no longer do it. And the problem is axiom number 5, which told us that the field is built out of harmonic oscillator creation annihilation operators. That assumed the field was free. When the field is not free, we don't know what to replace axiom 5 by. But we will very easily be able to write down Lagrangians that correspond to interacting theories. We'll be able to work out the corresponding Hamiltonians. And by using the correspondence principle, we'll be able to write down those interacting quantum field theories. So that's the reason why we've gone through this exercise. It's going to let us quantize interacting field theories. As a final comment, you might wonder, so we've now built the quantum theory by appealing to the Hamiltonian version of mechanics or of field theory. But you might wonder, can you get a version of quantum mechanics by appealing directly to the action and the Lagrangian description? And the answer is yes, you can. And that gives you Feynman's path integral. That's also something that we're going to look at, but we're only going to look at that in a few chapters' time. The path integral is going to be the simplest way for us to develop the description of interacting quantum field theories. Okay, the only thing left now is to discuss the exercises.